Hey, what's up, guys? Today I'm going to discuss an important topic from the branch of complex analysis, that is residues. So, residues basically help us to evaluate certain integrals in complex analysis, and with the help of residues, we can calculate some complex integrals in very easy and fluent fashion. So, before we start, we must know what actually Laurent series expansion is. There are three types of expansion that basically help us in complex analysis to evaluate different integrals. One is Taylor series expansion, another one is Maclaurin series, and the third one is written over here, that is Laurent series expansion. I'm not covering this topic very deep. I'm just overviewing it in a sense that we may able to solve a question regarding residues, and I will show that how to apply residue theory to evaluate a certain integral in complex analysis. So the Laurent series expansion of a function f of z is written over here. It is f of z in the Laurent series expansion form is equal to summation of n0 to infinity a n z minus z naught to whole power n plus summation of n1 to infinity b n z minus z naught to whole power n. So this expansion basically contains two parts. The first one with the coefficient an, and the second one with the coefficient bn. And the second one with the coefficient bn is very important, and it basically helps us to calculate integrals in complex analysis. And this b will help us to attain the coefficient, and this will further help us to evaluate the integral. So this bn has a general form. That's bn is equal to 1 by 2 pi iota integral of f of z dz over z minus z naught to whole power minus n plus 1. You must know. So the general form of bn, that is 1 over 2 pi iota integral of f of z minus z naught minus n plus 1. It is very important to know what actually z naught is. Z naught is the point around which we are expressing our function in terms of Laurent series, and you can see in the coming example that z naught is basically the point around which our function is not defined, and how it will help us to attain the solution of that particular integral in the coming example. So what actually residue is? Residue is the coefficient of b1. You can see that here it is written n. We have to put n equal to 1 here, and the function, and after putting n equal to 1 here, the coefficient of b1 is basically called residue. So what actually residue is? Residue is b1. When we put n equal to 1 here, we will get the residue that is called b1. So I can write it as b1 is equal to residue of that particular function f of z around z equal to z naught. Z naught is basically the point around which we are expressing our function in Laurent series, or we can say that the function, or the point where the function is not defined. So guys, we know that residue is basically the coefficient of 1 over z minus z naught, and represented as b1. So for finding what actually b1 is, we will put n equal to 1 in the general form of bn formula. So here you can see for n equal to 1, we will put n equal to 1 in the previous form of bn. We will get b1 equal to 1 over 2 pi iota f of z z minus z naught, and here it is written before minus n, so I will put n equal to 1 here, so it will become minus 1 plus 1 of dz. So after solving, minus 1 plus 1, you know, you already know that equal to 0, and something power 0 has answer equal to 1, so I'm just writing here f of z dz. So moving 2 pi iota over here, the final form becomes integral of f of z dz into 2 pi iota b1. B1 is basically called residue. So this is an important result. So this result is actually telling us that for any integral of some function f of z dz that contains some point z naught around which the function is not defined, we can evaluate that integral with the help of residue. First we have to calculate the value of residue, that is b1, which is actually the coefficient of 1 over z minus z naught, and then we will multiply it by 2 pi iota. After multiplying it with 2 pi iota, we will get the value of that particular integral. Now we'll see the example in which you will understand how this residue will work. So here we have the example. So we are going to solve the integral z square sine 1 by z dz, and c stands for here contour. Contour is basically the path or region around which we have to calculate this particular integral, and the chosen contour is here is modulus of z equal to 1, that is clearly indicating that it is a unit circle of radius 1 obviously. So we are going to calculate this particular integral with the help of residue theory around the contour C for z equal to 1, that is a unit circle. So before starting, we must know what actually the problematic points are. So for our region contour, that is a unit circle centered at origin 0 and having radius equal to 1, we can clearly see that the only problematic point is 0, because by putting z equal to 0 here, we will get sine 1 by 0, and that is actually undefined. So residue theory help us to evaluate these sort of integrals. So what we are going to do, we are going to express the expressions involving in our integral in the form of their series expansion. We have two expressions here, one is z square and second one is sine 1 by z. We are going to write the series expansion for sine of z. We already know sine of z is expressed as z minus z cube by 3 factorial plus z5 by 5 factorial minus z7 by 7 factorial plus so on. This is basically the series expansion for sine of z. As we can see, the question we have is involving as sine 1 by z. So in order to get sine 1 by z, we are going to replace that particular z by 1 by z in all the expression. So we will replace in this series expansion z by 1 by z, and according to our question, z square is multiplying here, so we will multiply after replacing z by 1 by z by z square. So I'm going to perform two steps directly. First is to replace in the series expansion of sine z by 1 by z. So I'm going to replace that z 1 by 1 by z, and that all will to be replaced by 1 by z, and after replacing we will get sine 1 by z, and multiplying it by z square, I am getting the result z minus 1 by 3 factorial into 1 by z plus 1 by 5 factorial into 1 by z cube plus so on. So you can work it out on your own by doing these two steps directly. So what actually z naught is here? Z naught is basically 0. I'm not writing z minus z naught or z minus 0 to whole power 3 or z minus 0 to whole power 5. That is not appropriate. But the z naught is basically 0 here, around which our function is not defined. Now we'll see how residue will help to evaluate this integral. So after replacing sine z by 1 by z and multiplying it by z square, I'm getting the following result here, that is z minus 1 by 3 factorial into 1 by z plus 1 by 5 factorial multiplied by 1 by z to whole power 3 plus so on. And I told you earlier in my video that residue is basically the coefficient of 1 over z minus z naught. So you can clearly see that here it is written 1 over z. Z naught is missing, that is 0, so it is not appropriate to write z minus 0. That is why I didn't write it here. So 1 by z is basically here, and the coefficient of 1 over z is called b1, that is actually our residue. So the residue b1 is 1 over z's coefficient, that is minus 1 by 3 factorial. So I told you with the help of residue we can solve the particular integral by multiplying b1, that is called residue, by 2 pi iota. So the value of this integral is equal to 2 pi iota multiplied by b1, that is residue. And in our case, for our integral, we have residue minus 1 by 3 factorial, that is the coefficient of 1 over z. So writing b1 here as minus 1 by 3 factorial and multiplying it by 2 pi iota, we get minus pi iota by 3. So that is our result. So the integral z square sine 1 by z over contour C, that is our unit circle with radius 1, is minus pi iota by 3. So this way residue help us to evaluate some integral. I hope that you guys apologize for my bad English, and do like or subscribe for more short videos. So after replacing sine z by 1 by z and multiplying it by z square, I'm getting the following result here, that is z minus 1 by 3 factorial into 1 by z plus 1 by 5 factorial multiplied by 1 by z to whole power 3 plus so on. And I told you earlier in my video that residue is basically the coefficient of 1 over z minus z naught. So you can clearly see that here it is written 1 over z naught is missing, that is 0, so it is not appropriate to write z minus 0. That is why I didn't write it here. So 1 by z is basically here, and the coefficient of 1 over z is called b1, that is actually over residue. So the residue b1 is 1 over z's coefficient, that is minus 1 by 3 factorial. So I told you with the help of residue we can solve the particular integral by multiplying b1, that is called residue, by 2 pi iota. So the value of this integral is equal to 2 pi iota multiplied by b1, that is residue. And in over case, for over integral, we have residue minus 1 by 3 factorial, that is the coefficient of 1 over z. So writing b1 here as minus 1 by 3 factorial and multiplying it by 2 pi iota, we get minus pi iota by 3. So that is our result. So the integral z square sine 1 by z over contour c, that is our unit circle with radius 1, is minus pi iota by 3. So this way residue help us to evaluate some integral. So in the end, I apologize for my bad English. Do like and subscribe to my channel. Thank you so much.